All right, off to example 3. So in example 3, we want to show that the slope dy dx is defined at every point on the graph 2y equals x squared plus sine of y. So keep in mind that slope is equal to dy dx, which is equal to m. All three of these things represent what? That's right. They represent a rate of change. Remember, the rate of change is slope, is dy dx, is y prime, is m, it's all those things. So we want to show that it exists at every single point on this graph. Now the points where it would not exist would be like a vertical tangent, if the graph is discontinuous, if there's a hole, if there's a jump, any of those things. If there's a corner, if there's a cusp, any of those things. So we want to show that it's not all those things. Well, to do that, we need to get dy dx, or again, the derivative, by itself. So I'm going to go ahead and take the derivative of both sides. So I'm going to write it out like the chain rule. It becomes the derivative of the inside times the derivative of the inner piece. So this becomes 2y prime times dy dx equals the derivative of x squared is just 2x plus the derivative of sine times dy dx. Right? It's the derivative of that inside piece. Again, the derivative of 2y times the derivative of the inside piece. So the derivative of 2y is simply 2. So this is 2y, 2 dy dx equals 2x plus cosine of y dy dx. So now our goal is to get all the dy dx's onto one side of the equation. So I'm going to go ahead and subtract this cosine y dy dx, and I get 2 dy dx minus a cosine of y dy dx is equal to 2x. And this is all very exciting because now, if you notice, we have this and this on one side. So I'm going to go ahead and factor that out and get dy dx parenthesis 2 minus cosine y equals 2x. Now as you can see, I have this all right here. So all I need to do now is divide both sides by 2 minus cosine of y. And I get that dy dx is equal to 2x divided by 2 minus cosine of y. Alright, good. Now we just gotta stare at this for a minute and try to understand how in the world does this tell us that the derivative exists everywhere? Well, this is a fraction, and the only thing that can make a fraction undefined is if we have something like 0 over 0, or 0 over infinity, or basically if the denominator is equal to 0. So all we gotta do is find out that value that could make that 0. So we just set the denominator equal to 0. So you get 2 minus cosine of y equals 0, and you get cosine of y is equal to 2. Now let's just stare at that for a minute. Can cosine, the graph of cosine, I know it's of y, but here's the graph of cosine roughly, and here's 1 and here's negative 1. Can we ever get up to 2? Well, no, we can't. So this is never true. So here's our conclusion. Since cosine of y is between negative 1 and 1, and when I mean the cosine of y, I mean the outputs, and 2 minus cosine of y can never equal 0. Therefore, dy dx is defined for all x and y values. Now the reason I don't have to check x is because x is in the numerator, so I can plug anything in and it'll work. Okay, so that's how you prove that the derivative is defined at every single point.